Hey guys, welcome in. Um, got 9:03 on the clock here. I'm checking attendance. Things look okay with first and last names. So I think this will be our last spotlight session of the week, given the holiday week. And it's certainly a cold day out there tonight. Um, I got a fire burning over here, so if you hear some popping and cracking, that's what that is. And just kind of enjoying a nice Tuesday evening. Um, so, how's everybody doing in regards to the class? I've been kind of starting this off asking folks that what chapters we're visiting or what chapters we're doing this week. And the reason why I'm asking this is it's really because we're kind of starting to enter the review portion of the semester, right? So this is kind of where I like to open it up and see what we want to talk about tonight, if anything, and kind of go from there. So go ahead and chat me something in if you don't mind of what chapters we're checking up on, and we can take it from there. Hey Kelsey, what's up? The brain, okay. Yeah, Kelsey, we kind of started that up last night. I didn't finish it, so we'll probably do that tonight. Lindsay seconds that and says the brain too. Uh, all right, Cassandra. Well, let's keep that B. That's always great. It's hard to move up letter grades. So when let's make sure we retain that B, and maybe we'll even bump you up to maybe 87, 88 in case they want to curve the class. We can kind of get you in that gray area that maybe you could be considered for an A. You never know. It just depends how things shake out at the end. So, do we have any other topics that we want to discuss tonight? You all talk about a final exam, which tells me that's comprehensive or that's over a set amount of chapters. Okay. Autonomic nervous system, the optics, and auditory. So Haley's got a comprehensive final. Kelsey's got a comprehensive final. Mackenzie has a comprehensive. Holy smokes. Okay. Comprehensive all around. Lauren too. Okay. Cassandra says lecture 4 exam. Okay. So guys, I think this is kind of when we need to start touching on different topics. Okay. Now we can go over the brain tonight and definitely hit on the different lobes. That's more than okay. But I want to try to utilize our time as much as possible. Yeah, Haley, you'll have to remind me what chapter 15 is. I can't keep these chapters straight. So when we're going over topics, let's remind me of what we want to go over. Okay, I'd like for you all to kind of try to put my legs up here. Excuse me. Okay, sure. Yeah, we can definitely touch on the autonomic nervous system and visceral reflexes. I think that's going to be included in the PNS system. Um, okay. Is there any other topics that we want to discuss tonight? We'll probably talk about lobes. Lobes are good. Um, We'll talk about PNS. How about muscle contraction, muscle relaxation? Yes is in talk about it, or yes is in we're good? Okay, that's cool. What about action potential? Sodium, potassium coming in, how we send electrical signals. All right, cool. Well, sounds good. Thank you for the feedback, Kelsey. You might have spoken for the whole group tonight. All right, I'll ask again. Maybe we'll get some more feedback. All right, well, we've had some folks come in. Okay, the signal sent to the cerebellum for motor and unconsciousness spelling. Oh, you're fine. I think I get it. Okay, we'll do that when we do the brain lobes. Okay, so last night we kind of started the brain lobes and we didn't finish. And what really has to happen is that we kind of have to get an idea of what's going on in different parts of the regions of the brain, different regions of the brain. And when we're able to figure this out, that can really we can really start connecting the dots of what happens when things change. Pathophysiology. What happens when we drink too much? What happens when we smoke a little pot? What happens when we take a little cocaine? Stuff like that. If we can understand what's going on in the background and then we can alter that, then I think students kind of understand what's really going on and how the brain is becoming affected. So let's start off with the frontal lobe. The frontal lobe really deals with decision making. Okay, decision making and the fact that we are decision making and personality is probably the big ones. Decision making being in the prefrontal cortex, right? Which is literally like right here. And then we have the personality of the frontal lobe, and then mainly we'll talk about the motor cortex, which is at the back. But one of the last things to develop in the brain is the prefrontal cortex. And this just so happens to be the part where we do decision making, particularly in males. And I mentioned this last night, we've always heard that when we get our driver's license, car insurance tends to be a bit higher in males than it does females. Well, one of the reasons for that is that the prefrontal cortex in males are a lot. Yes, that's right, Cassandra. Yes, you might have heard me talk about this before, or maybe you knew that from somewhere else. Age 25, and you know what? It may be 25. I hate to admit that, being a male myself. Just finding out that I'm going to have two boys. So yeah, definitely, yeah. Psychology 110 is we'll share that. So the thing about psychology is that it really goes over the neurobiology, neurophysiology of the nervous system. And a lot of you all who have taken Psych 110, and I did too when I was a student, you really get a really cool background from a psychology perspective versus a biology perspective. Very interesting class. So yeah, I would say about 22, 23, but you're probably right. I think 25. And I don't think my insurance dropped off till I was 26. Okay. And then it starts to lower. And the reason why is because males tend to take on more riskier behavior. Okay. Riskier behavior, and the fact that uh, uh, it's hard to, yeah. Oh, it is. Yeah, definitely. You have to keep it separate. But it definitely compounds on each other too. Excuse me, my nose is itching. So the prefrontal cortex mainly is about decision making. Very late in development, particularly in male adolescents, juvenile males. That's why their risk behavior becomes a lot higher. They pay a much more higher premium in insurance too because of that. So Personality, a little bit of emotion also is in the frontal lobe. Um, and then in the back of the frontal lobe is what's called the motor cortex. Now, the motor cortex is really what carries out the movement, gross movement, okay? Climbing a ladder, walking up the stairs. Yes, walking, even though we're not really thinking about it, we're just walking. This is the most. Sorry. So maybe I'll just scoot this a bit up higher to my voice. Okay, thank you guys for catching that. So let me rewind and say when we're really talking about mowing the grass, doing this, right? What's it called when you tap your hand? Let's see. I think it's tap your head and rub your stomach. Those are your. That's a lot of motor cortex. It's also your left and right hemisphere trying to decipher what's going on. Some people can do it. Other people can. What is it? Tap. I think it's this where you tap your head and rub your stomach. Okay, with your right hand is tapping, left hand is rubbing your stomach. If you're left or right brained, that may be a lot easier versus doing this. I think as you notice that I'm actually moving my hand as I tap, and barely moving my stomach on my right hand on my stomach, and that's just because I'm probably more left brain than right brain. So that deals with a little bit of motor cortex too. Behind the motor cortex is when we get into the parietal lobe. Okay, one of the more larger lobes in the brain region, and it does a lot of different things. But the main takeaway from the parietal lobe is the somatosensory cortex, which just so happens to be right behind the motor cortex. The motor cortex in the frontal lobe, and then right behind it is the somatosensory cortex. Okay, and this is what happens when we have sensory come in. Okay, everything from me feeling the heat on this fire to a big bulging zit maybe on my forehead to a piece of glass that was stuck in my thumb when I tried to do some home improvement a couple months or a couple weeks ago that's just now healing. And what's really happening is whether it's pain neurons, pain fibers, or just sensory neurons, is that they all come up, excuse me, part B, they all come up to the somatosensory cortex. All right, and what I mean is they come up through sensory afferent neurons. Okay, sensory afferent neurons, not, of course, motor cortex. I didn't mention this is motor efferent neurons. Motor efferent neurons, not sensory afferent neurons. So that is something that always tends to show up on exams from time to time is when they throw out some vocabulary terms. And let me just type these in because they sound almost alike. Okay, and then the acronym is same. So sensory afferent, motor efferent. Sometimes instructors will ask you what's if information is being carried on a efferent neuron, what is it carrying? Well, that means it's carrying motor information, right? Something that's going to innervate a muscle to contract and carry out some kind of motion. All right. If the information is being carried on a afferent neuron, then what is it carrying? Well, it's carrying sensory information, sensory afferent. So this is one of the big things that you want to try to figure out. So when we're dealing with that, what we need to figure out is where all these are going to, and that's kind of, we'll get into peripheral nervous system, excuse me, parasympathetic nervous system and sympathetic nervous system. That's part of the autonomic nervous system. We'll talk about that next. But before we do, let's talk about something called the homunculus. And I'm going to try to spell that out as best I can. Has anybody ever heard of the homunculus? It's actually a theory or a concept. And if you don't know, just put question marks or something so I know you're listening. Okay. All right. Thank you, Cassandra Haley. Lindsay, thank you. We got 12 people, so I really want to kind of get some feedback here. Thank you, Mackenzie. Kelsey. All right. That's cool. I can live with 5 or 6 people. All right. Thank you, Lauren. So what this is, and sometimes it's covered, sometimes it's more covered in 139. The homunculus is such a goofy term, but what it really is that it explains that the somatosensory cortex that really comes from the crown around, okay, around the head. And what it does is that it maps out, it's like a map of the amount of, let me just, sorry guys, my wife is so loud, I'm going to shut her door. All right, I apologize. Okay. So what I'm trying to explain is that the homunculus is really about dedicated space on the somatosensory cortex, that space dedicated for sensory, okay? So we all know that there are more sensitive areas on the body than not. Lips, face, neck, genitalia. All right. Other areas too that I'm not thinking about. Forearms, maybe. And so bottom of your feet, ticklish, right? So these areas, maybe your ears can be a bit sensitive too. And what this means is that there is more space dedicated on the somatosensory cortex for these areas, okay? Because these just so happen to be the more sensitive areas versus something like on the back, on your lower back, on the back of your thigh, on your shin, somewhere that, we don't feel sensation as much. If somebody were to take 2 needles and just rest them on your back from a certain distance away, you really won't be able to tell if that's 1 needle resting or kind of showing pressure on your back, or if it's 2. Obviously we don't see it, we just feel it. Now, if somebody puts 2 needles and I'm closing my eyes and puts them on my forehead, I can tell there's 2 different pressure points because my face is more sensitive. All right? Does that make sense? Right. Makes a lot of sense, right? We all know the sensitive spots. I think the neck, what is it where sometimes females or males get hickeys on their necks, and there's that one spot that folks just go crazy on. Well, think about the homunculus. That'll make you remember things. That's probably one of the better examples I've had in a while, but I think there's a lot of truth into that. So let's just move on before I take this down another path. The occipital lobe. Okay, the occipital lobe is the back of the brain. Okay, the back of the brain where it's really dedicated towards vision. All right, this is where I'm sure you've learned about cranial nerves, right? Well, cranial nerves, one of the cranial nerves is the optic nerve, and the optic nerve travels from obviously your eyeballs all the way back to your occipital lobe. it'll actually crisscross too, kind of almost towards the back. So what that means is that your left eye, well, it's more receptive fields. It's not as much as your eyes. It's your receptive field. So both of my eyes over here will be processed on my right side, and the receptive fields over here on both of my eyes will be processed on the left-hand side, and they cross over. So, Anna, I just saw your question, small human. I wish I would have seen that earlier. I would have, I could have. Oh, you're talking about what the homunculus is. That would be like an ecology Homo sapien or Homo sapien sapien. That's very clever. But I think I know what you were getting at. Yeah, that's all right. That's cool. Yeah, I'm trying to remember what the prefixes are for that, but I can't. I'm not going to embarrass myself. Ecology was never my thing. I got a C in ecology. So with the occipital lobe, the interesting thing about the occipital lobe is that it has the lateral geniculate nucleus. Lateral geniculate nucleus. And you'll probably talk about this a little bit, or at least the bipolar cells and photons and other cells that we won't dive into too much conversation. We won't dive into too much topics with that, because I think that's more 139. However, with the lateral geniculate nucleus, the interesting thing is that, and you probably learned this too in Psychology 110, is that there is a window that children learn to develop their vision or their interpretation. Okay, I cannot think of what it's called, because it's I can probably pick it out if you gave me multiple choice. But the point is that there's a crucial time in development, either between ages 2 to 4 or 2 to 5, where the lateral geniculate nucleus is being developed, and it's being developed through vision. Okay, there's been really unethical tests done in the distant history, in the distant past, where scientists would put a patch over a child's eye. Okay, and basically what has happened is that you would see the difference in the lateral geniculate nucleus from the eye that is able to see and the eye that it was patched up. And it was a huge difference of tissue development, where these children were basically lost their vision for good in one of the eyes, because of whatever reason they participated in this experiment, and it's irreversible. So it is crucial, when we see babies or toddlers with all this sensory overload, particularly I think there'll be probably tests or experiments done with iPads. A lot of children have iPads, right, where they play their games, and that's a hell of a lot more stimulation and sensitivity coming in than what we had when we were children, right? I mean, we got some blocks and some Legos and maybe some stars and planets that we saw, nothing crazy. Now you get a TV screen 10 inches away from, 10 inches wide, 12 inches away from your face, and you're racing a car with a bunch of other ones, like playing like Mario Kart, right, at age 3 or 4 or however long it is, and they're moving things with their fingers. And the point that I'm trying to make is that the brain development will probably be much more advanced at that age than it ever was when we were children. Okay, very, very fascinating is when that happens, and that's all because of how what we see really drives the occipital lobe. Any questions about that? All right, cool. All right, thank you guys. Temporal lobe, okay? Temporal lobe is hearing, okay? Right? That's my little drum up to an interesting climax. It is hearing. So for some of us who just kind of went over ear, or maybe the anatomy of the ear, anatomy of the eye, you probably don't understand a lot of the physiology behind it. Okay, you might have gone over a little bit of the anatomy and blah blah blah. Anatomy is cool, but physiology is really where we apply things. We apply application. Okay, and what happens is that we hear things through sound waves. Okay, believe it or not, right? And the pinna, this is called the pinna, our ears. I have small pinnas or regular size pinnas. I'm not like Dumbo. However, it is designed to filter in these sound waves into the ear, okay? Into the ear. And as sound waves enter, they tend to vibrate the three bones in the ear, the stapes, the incus, and something else. I can never remember it. Does anybody know the third bone in the middle ear? Ah, thank you, Kelsey. Malleus. You're right. It's like the bone and stirrup, right, or something like they call. I never understood that. Incus, stapes, and malleus, and they oscillate back and forth very carefully, right? Because these sound waves are been kind of concentrated into this little space. And as they oscillate, they open up a cavity into the oval window. And inside the oval window is the inner ear. That's where the hair cells are. And think of it as like a rounded U, okay? And inside this rounded U is a bunch of fluid. And living in this fluid are hair cells lined up like this, all the way around this U. And as these sound waves come into the oval window, they move this fluid back and forth. And as this fluid moves back and forth, it causes the hair cells to sway back and forth. And when they sway back and forth, they release an action potential, right? Action potential, we probably remember that from chapter 4, chapter 3, whatever it was. It's one of the more cornerstones of physiology. This is how we send signals in the body. And these hair cells will send an action potential through the auditory nerve, and it will synapse in somewhere in our temporal lobe, and that's how we interpret sound. And the best way I can explain this is we've all seen, like, Discovery Channel or History Channel or Animal Planet, probably Animal Planet, where they have these documentaries on, the Great Barrier Reef or something like that. Reef, so I should say. And you've probably noticed that when you have current kind of going through these reefs, you have seaweed that kind of sways back and forth, or different sea urchins or whatever, and you can kind of see that they flow with the water current. Well, that's kind of how hair cells are, right? And as they bend and flow, they send signals to the temporal lobe, and that kind of dictates how we hear things. How we interpret is a completely different thing. But I'm sorry, guys. Let me just get this. This is my grandmother real quick. I apologize. Hey. All right, guys. Sorry about that. Make sure when she's 86 and she calls you at night, you just got to answer. So when you have the temporal lobe, and when we interpret sound, that's more the psychology thing when we get into language. Okay, this is another thing back in development where we may talk to children or try to enunciate words so they can hear it and then respond back. That's what that's about. Okay, it's about learning to understand what these words mean, what they sound like and then having to enunciate it and sound back. That's more like Wernicke's and Broca's area, which we won't dive in too much of that. So what we've done there are the lobes. Those are the big parts. I'm assuming we don't have any questions about that. So let's dive into two other tissues that I want to talk about. And one is the cerebellum. Well, we can get into the rest. We can go into like amygdala, pons, limbic system, hippocampus, thalamus, hypothalamus. We may do them all. We'll just have to see. Back to somebody's point. Somebody talked about the cerebellum. Cassandra did. So Cassandra was talking about the cerebellum. Does anybody know what the cerebellum is responsible for? Yeah, it's balance. Thank you, madam. Balance. The cerebellum really is the first brain tissue that's affected by alcohol. So when we drink too much or we feel a little bit loopy or we lose our balance, alcohol, ethanol is really what's targeting. That may be decision making. That may be decision making is what you all are talking about. If you're talking about, I'm talking about balance, and it could, I guess, like if you're, like it could cloud your judgment. Okay, with decision making, definitely a lot of things can. But if you're really talking about, stumbling around, not being able to be very coordinated, that's your cerebellum, and that's usually the first to go. I'm sure your frontal lobe or your prefrontal cortex is affected by that too, but it's much more down the road. The first thing to get to come under the influence of alcohol is your cerebellum. If we've ever been privied to a sobriety test, okay, where we go through a checkpoint and they suspect that you have been drinking or yada, 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 they'll pull you out of the car and they'll want to make you touch your nose, follow the finger, stand up on one leg, things like that. What they're really testing is your balance, your function of the cerebellum, if there's any alcohol involved. Now, granted, this is a very subjective test. And what I mean by subjective, I mean it's very opinionated, okay? There's not a lot of factual behind it. You might as well be taking a lie detector test. It can be picked apart in court time and time again. What really nails you to the wall is your breathalyzer. Okay, that is scientifically backed up. The sobriety checkpoint, or the sobriety test, or I should probably say sobriety field test, is really testing the function of your brain under some alcoholic influence. The eyes, I think, if the eyes could be affected, if you can't hold your if you're so inebriated you cannot, your eye muscles tend to flicker and you won't be able to sit and stare at a finger for a long period of time, concentration. That may be what you all are explaining about, Mana, with the frontal cortex. They'll see if your eyes are either constricted or dilated. I think they're never going to be constricted. That's more like cocaine or a stimulant. Alcohol is more a depressant, and I think if I stand corrected, that your eyes will be more dilated because they're a depressant. Alcohol is considered a depressant, so your eyes will be dilated or relaxed. The eye muscles will be relaxed, causing your eyes to dilate, your pupils to dilate. But don't quote me on that. So that's the cerebellum is a big deal, only because we know what's going on if we've drank too much, particularly balance. Your basal ganglia. Does anybody know what the basal ganglia does? Yeah. Yeah, man, I'd say motor control. That's what really initiates the motor. I talked about gross. Um, yeah, behavior too. More like initiation of motor control. Now, we've spoke about the motor cortex really doing the gross movement. The basal ganglia really will initiate the movement. That's what gets things going. Does anybody know what happens, the disease that develops when the basal ganglia becomes diseased? What neurodegenerative disease is that? If you don't know, I'll give you a hint. Yeah, that's right. It's Parkinson's. Very good. Parkinson's, if we know, has the tremor, right? The tremor, shuffling of the feet, uh, a lot of that. And right, Cassandra, you're right. So the basal ganglia really will allow me to do this. Okay. Now, caffeine, you may see a little bit of flickering, but if you sit there and you can hold your hand out and see how still you can hold it, that basically means that the basal ganglia is controlling that. The basal ganglia will control unnecessary movement. Okay. Sometimes we'll get a muscle twitch here and there. That's okay. We've all done that, particularly if we've been working out. I got on the treadmill for the first time in a long time because I about had it with the way I've been feeling. I need to get some exercise in me. And I was twitching throughout the night a little bit, particularly in my hamstring and quads, just because I'm out of shape. That happens. That's not as much as the basal ganglia. That's just a rare action potential getting out and initiating muscle contraction. So what has to happen is the dementia. It's a good question, Cassandra. Dementia, from what we know, deals with memory, right? So when we're talking about memory, we're really talking about probably the limbic system and I'd say it's the limbic system. It's not the hypothalamus, that's endocrine. Thalamus is more the relay station. So when we're talking about short-term and long-term memory, we're really dealing with the limbic system. The limbic system, does anybody know what else the limbic system does? That's your emotion. Okay, your amygdala is emotion. Okay, the limbic system is, the amygdala is part of the limbic system, so it really deals with emotion, how we feel, happy, sad, angry, depressed, that's a lot of that. Lots have to do with neurotransmitters too. Yes, yes, Manna. From my understanding, it does. But I don't feel too confident about that because you can control what we're talking about. We're talking about voluntary movement. So if it's involuntary, that's going to be more autonomic nervous system. We'll talk about that next when we have time. But basal ganglia really is well, it could probably do a little bit. I mean, I think there are some subconscious things that go on that the basal ganglia will suppress. Okay. Like, maybe like a little bit of handwriting. I think handwriting deals with a lot of a little bit of basal ganglia and cerebellum. Okay. But there's a lot of things where you have some rogue action potentials that get out, and the basal ganglia will help suppress these so they don't cause you to become uncontrollable. So it may be an answer of both voluntary and involuntary, because nobody sits there and like wants to tremor, okay, or shuffle their feet, okay, when they're trying to walk, which means they don't really pick up their feet. They just kind of shuffle them as they go by, and they're kind of hunched over. Those are the key things to Parkinson's. It's really been quite a success story on treating Parkinson's nowadays. We won't go into that. That's a really cool story. I told that story about 2 weeks ago. But we can do that another time unless you all are really interested. So it's all really deals with the basal ganglia. And limbic system is emotion. Amygdala is emotion. Pons and medulla. What do we know about those? Yeah, that's right. It's breathing. Breathing and sensing the pH in our blood. Baroreceptors, chemoreceptors, they tend to be found around the pons and medulla. So if we hold our breath, you may realize that we can only hold our breath for so long until we gasp for breath, right? What's really happening is that we are selectively telling ourselves not to breathe in. All right. Well, we still have metabolism going on, which gives a byproduct of carbon dioxide, which is building up in our system. And eventually, there's so much carbon dioxide in our body that it'll override our um, uh, stimulation or effort to hold our breath. Right? I mean, unfortunately, this is how you drown. All right. I mean, if you're underwater for X amount of time, eventually the urge to gasp. Good question. I'll have to answer that next. When the urge to gasp for air occurs, you inhale water, and that's such a terrible way to go out. I've always feared of death by drowning, but that's what happens. Is that there's so much carbon dioxide that lowers your pH in your blood, tells your chemoreceptors that you have to take a breath, and then even though you're holding your breath as much as you can, that the chemoreceptor will override that and will allow you to draw air in, and that's it's kind of like a safety valve, and hopefully you're above water at that point, so you can gasp for air instead of water. So if the pons is damaged, the pons really does your breathing as well as your sleep center too. Um, I think what happens is the same thing. I mean, people who have sleep apnea, right? Eventually, at some point, they gasp for air, right? Because sleep apnea is when somebody who doesn't breathe normally when they're sleeping. It's like something. Maybe the pons is damaged. I can't remember what really causes sleep apnea. It could be the pons, but what really happens is that it will. I'll tell you what, I'm a popular man tonight. I'm never this popular on a Tuesday. Um, what happens is that it it allows something overrides the pons that allows you to gasp for air, and it may be the same concept. It may be the medulla doing that. I don't want to speak on it too much because I'm not sure, but eventually it's the same concept where the CO2 grows in your blood, and then it kind of wakes up the respiratory center to trigger a breath. Okay, lowers the diaphragm, sucks in air. Obviously, we get oxygen carbon dioxide exchange, and then we can kind of raise our pH level back up to 7.4. That's I think it's mostly driven by pH in your blood, right? And then just the need for oxygen. That's what affects the chemo and the chemoreceptors. Not as much baroreceptors, more chemoreceptors. So I think in a roundabout way, I hope I answered your question, Mana. And that's a difficult one. No, because they compensate for it. So you could say that if obese people, if this is what you're thinking about, if this is your logic, obese people have more metabolism going on because they have more cells, then they would create more byproduct carbon dioxide. if they have more carbon dioxide on board, then the pons or the medulla or both will compensate for that, and they will just breathe either a little bit deeper or their respiration rates will be a little bit more higher per minute. Normally, it could be 12 respirations per minute. For people, I mean, if you're going to say obese people are out of shape, which means that they have to move more oxygen, then you could say that. You could say that they are probably likely more out of shape, which means their heart has to work a little bit more, which means they're pumping more blood and therefore they're pumping more oxygen. So I hope that answers your question. It's a compensatory mechanism. Okay, cool. Yeah, so the interesting thing, Cassandra, with COPD is, COPD, the thing about the lungs have elastic fibers in them, okay? There's also called pulmonary fibrosis, which is opposite of COPD. What is it? What is COPD? Something obstructive pulmonary disease. Comprehensive obstructive pulmonary disease, whatever it is. So what happens is, particularly this happens when people smoke. The smoke over a lifetime will damage the elastic fibers in the lungs. And so what happens when we breathe, I should probably just explain what happens when we breathe. When we breathe, we send a signal down to the diaphragm to contract, right? There you go. Chronic. That's what it is. It's chronic. Thank you, guys. Chronic. Over a lifetime. Remember? No, you can. My father-in-law, I think, has a bit of COPD, only because his daddy smoked in the house when they were kids. So it may be secondhand smoke. It could be genetics too. But what happens is when we breathe in, the diaphragm will contract. And what that does is that creates like a negative pressure, which allows air to easily be inhaled in, right? It's like drawing a syringe, right? We're kind of pulling the syringe back and you see it filling up with air or something or water. It's the same thing with lungs. And what kind of allows this to happen or helps it happen is that the lungs have this elastic fibers. So when we exhale, yes, the diaphragm relaxes, but the lungs that are now filled up with air, the elastic fibers recoil back, causing a positive pressure and allows us to easily exhale. All right, we've probably always noticed that it's a little bit harder to inhale than it is to exhale, right? When you want to calm down, you go, and it just kind of comes out, right? There's no effort. I mean, there is an effort. You can make yourself blow out harder, but air will exit your lungs with no work, right? It's like, okay, try that out. If you just relax, the lungs actually recoil and allow air to exhale on its own. Well, what that is, that's the elastic fibers in your lungs, all right, that kind of recoil back to normal and allows you, at the time when they're kind of at a resting state, there's no air in your lungs, or very little. With COPD, the smoke damages these elastic fibers. So all of a sudden, your lungs that have no air when they should be here, they're like way out here. They're a lot farther away. So when it's time for you to inhale, you may be able to only inhale halfway because your lungs are already stretched out, okay? Because it has damaged elastic fibers. It's easy to recoil. It's easy to you'll have to force yourself to blow out if you have COPD. You have to like blow it out, right? But if it's much harder to get a full breath when you have COPD because your lungs are not recoiled in. The elastic fibers have been damaged and they're much farther out, and they can only expand for so much, right? It's not like we could just keep on expanding. And anyways, the point I'm trying to make is that you have to force the air out to get a full breath in. That makes sense. Pulmonary fibrosis is opposite. That's when there's too much elastic fibers, and it's a lot harder to inhale. Yeah, pulmonary fibrosis is more rare. It's COPD is more environmental thing. That's smoking basically, and some of it's genetics. Sorry guys, my nose itches tonight. I don't know if I'm getting a little bit of drainage or what. All right, is there any other questions? It's 9:53. Thank you guys for the questions. It certainly helps these spotlights go by fast. Any other questions before we break? So we covered lungs. None here. Kelsey, you usually show up most nights. We may have to do your muscle contraction, muscle relaxation when we rejoin next week. I think you were the one that said muscle contraction, muscle. No, you said autonomic. No, you said muscle contraction. We'll have to do autonomic nervous system, Haley, and muscle contraction, muscle relaxation probably next Monday, because this will be our last spotlight for the week. Now, if you're pressing, you can always just give me a call. Yeah, let me just go ahead and throw this in here. I did this the other night. So that's my number. Yeah, that's all right. It does that. It mutes me. It kicks other people off. It sucks. That's my number. If in case we need to talk about stuff right now, just give me a shout and we can have a one-on-one on some stuff. But other than that, guys, that's all I have prepared tonight. About run out of time. A very, very happy Thanksgiving to everybody. If you are traveling, be safe. I'll be making my way down to Somerset, and probably hope to see you guys back Monday evening, where things are going to go awfully fast when the semester's done. Yeah, Lindsay, thank you. You too. And we'll catch you guys next time. Yeah, thank you. Thank you for your participation, man. I loved it. Yeah, you too, Madeline. Thank you. I can, Cassandra. I can. If you want me to throw this one up, I can. I usually just I let you all tell me, and I can put it up if you want. Okay. Do you want me to put this one up? Okay. Yeah, I can. I'll do it. Let it load to the system, and then I'll load it to YouTube. Oh, you're fine, Abigail. We'll catch you next time. I know how that goes. I came home at 6:39. Long day. All right, guys. Take care. Happy Thanksgiving. You're welcome, Jade. That's why I'm here. I'm glad to hear that. Thank you.